Hello and welcome to the Revision Village study sessions for October 2023. This is a session for applications and interpretation, the higher level. We'll be starting in about 2 minutes. Just waiting for people to join up. If you've joined up already, just make sure you have your calculator that you would use in the course with you. And if someone doesn't mind, if you could just in the chat box, just put a yes if you can hear me okay and can see the screen showing the title page for this session, that would be great. Thanks. Thank you, Tarek. So I can be heard and the title page can be seen, so that's good news. Yeah, Tarek, I was going to mention this when we start. So I'm going to go through the process and show it on the screen because we're going to be changing between polar and rectangular a few times during the session and changing between radians and degrees. But if you have it in polar mode for a start, that's the best mode, I guess, to have it in at the start. Yeah, because we're going to start by at some point at the start putting a number from rectangular form into polar form. So yeah. Okay, just going to wait about 1 minute and then we'll make a start. Yeah, just remember, Tarek, when you're watching the videos, don't ask questions to the screen because you won't get a response. Okay, we'll make a start because it's just ticked over the hours. So welcome to the Revision Village study sessions, October 2023, and this session for applications and interpretation higher level on complex numbers and sinusoidal functions. Just before we start, just a reminder to make sure that you've got your calculator with you that you're going to use during the course and in the exam. As we used on the website in the videos, I'm using the TI Inspire, the Texas Instruments calculator. So if you've got that, then you'll be able to do exactly what I do on the screen. Eric had just asked what mode should the calculator be in, and I'd mentioned we're going to change back and forth between rectangular and polar a few times during the session. So and we'll go through the process the first time we do it. If it's in polar mode at the start, that's fine. We're also going to change between degrees and radians during this because when we're dealing with polar form, you should have your calculator in radians mode, but sometimes you'll get a sinusoidal function question that's in degrees. So you definitely need to be aware of changing that back and forth, and that's a really huge thing in the exam too. And also before we start, you can ask questions at any time. If it is if it makes sense to answer it live at the time, I'll do that. If I think it may disrupt the flow, I might just say to you, I've seen your question and I'll answer it at the end. But I'll definitely make sure we answer all the questions. So there's a question and answer box you can use, and there's also the webinar chat box I think you can use as well. But if you stick to the question and answer box, then it's easier for me to manage from there, so I can put them as answered or dismissed as we go through them. And there are no unreasonable questions, so feel free to ask anything. So yeah, this is a session on complex numbers and sinusoidal functions. And just to note here what we're going to be going through today. So we'll review conversion between Cartesian, polar, and exponential forms. For some people, this may be review. Depends if you've got to this point in the course, it will be review. Some of it may be new to you, but we cater for all. We're also going to look at products, quotients, and integer powers of complex numbers and how we can use the calculator to help with those if it can, and sums and differences, so plus or minus, and also noting on the right-hand side here then, particularly sums and differences as they relate to sinusoidal functions. So it's a big part at the top end of this course, looking at sums and differences of sinusoidal functions and using complex numbers to do so. And we'll look at 2 or 3 questions. And the questions, I've tried to include one that's a kind of a paper 1 type exam style question and a paper 2 exam style question. And we'll look at some calculator techniques in here. And again, these may be useful to you if you've not seen them before, or if you're using a TI Inspire. Otherwise, you may have to consult your teacher if you're using something else like a TI-84 or a Casio. Okay, so just moving forward a little bit, just showing the formulae here off the formula sheet. We don't get a lot of formulae on the formula sheet for complex numbers. We just get told that a complex number can be written as z equals a plus bi, and that's of course rectangular form, where a would be the real part, which would be a movement along the real axis, and then b would be the imaginary part, so a movement in the upwards or direction of the imaginary axis. And then we also get these are both actually modulus argument forms because they are expressing a complex number in terms of its modulus or argument. We tend to call the first one here polar form, r times the cosine of theta plus I sine theta, and the second one we call exponential form. Or we can call it Euler form, noted here, named after Leonhard Euler. He's a mathematician from about 300 years ago who came up with this, one of the greatest mathematicians of all time. So we have polar form and exponential form. I'll try to stick to those two just so there's no confusion. Jim has just asked, when plotting the complex number, do you need to draw a line to the point or can you just label the point? That's a good question. And I would always draw a line with an arrow to the point. Yeah, it's not 100% necessary. You're not going to get into trouble either way. I can say that for sure. I always like to think of complex numbers in terms of like a vector movement from the origin. And it helps me understand them geometrically, particularly if you're plotting one in an exam. The reason you're plotting it is to do something geometric with it, which usually involves adding or subtracting something or multiplying it and see what movement happens. Although, having said that, there are a lot of questions where you might just get a geometric shape and they give you 3 or 4 complex numbers, which are the vertices of that triangle or square, and they ask you questions about the area or the side lengths. So you don't have to draw the line. You can always just put the point. And I might even say, treat it in context. If you're doing something about a geometric shape, it might make more sense just to put the points, because then the arrows are just going to get in the way. But if you're doing something to do with arguments or moduli or how something is changing, that might make more sense to put in the arrow. But you're not going to get into trouble either way. So hopefully that is helpful with that one there. Right, I'll just tick that off as answered. So yeah, so these are the formulae we get, and just quickly showing the relationship between these. So we have, first of all, in rectangular form, a plus bi, and just showing here we have our real part and our imaginary part, and they always form a right angle triangle, of which they create this angle theta, which is the angle measured anti-clockwise from the positive real axis. And so we can just use basic right angle triangle trigonometry to find out things like what we call the modulus of a complex number or the distance away from the origin. And that's always going to be using the Pythagorean theorem. Just noting here, the modulus of a complex number would be the square root of a squared plus b squared, the real part squared plus the imaginary part squared. And then we have before we mention the argument, just noting here, this is the relationship between that and modulus argument form. We always have the value r shown there, and that's always the modulus of a complex number. So in modulus form, r is the same as square root of a squared plus b squared in rectangular form. So Cassandra's just asked, I was just wondering generally in this course if we use the rounded answer or unrounded when solving subsequent parts. Okay, so I'll just quickly answer this question because it is useful. So yeah, you can always round to 3 significant figures at the end of a part, and then you can use that rounded part for the rest of the question. You'll never get penalized for that because you can always use 3 significant figures at the end of the part of a question. So no worries with that at all. What you just need to be careful of, and this isn't really what you're asking, but don't round ever to 3 significant figures when you're in the middle of a part of a question. So always have at least 4 significant figures until you get to the end of a part of a question. And then, yeah, but as long as you've rounded to 3 significance at the end of the part of the question and then move to part 2 or part 3 or part B or part C, there's no problem with that at all. And when you see the IB marking schemes, they always note that they'll always have notes for markers. In part B, they'll say, you could expect this answer if they rounded at the end. You could expect this answer if they didn't round. And then the markers just have to know everything in between in case they did round or didn't round. So, yeah. We tend to, on the Revision Village website, when I make the videos, I tend to, at the end of every question, round to 3 significant figures and then use that in the subsequent part, because I think that's what most students are going to do, or what their teachers are going to tell them to do. Okay, so yeah, we've just connected there the modulus of a complex number between rectangular form and polar or Euler form, and then just quickly checking, again using right angle triangle trigonometry, the angle theta here, which is called the argument of the complex number. The tan of that angle would always be opposite divided by adjacent. So the tan of the argument is the imaginary part divided by the real part. Therefore, the argument itself will be the inverse tan, just shown here, of imaginary divided by real, or the inverse tan of b divided by a. And just noting the connection there, so the argument of the complex number in polar form exists inside the cosine and sine functions, and in Euler form it exists inside the exponent there. So those are all the connections. And if you know that and understand that and remember that, you can always convert between the three, whatever situation you're in. Although there are ways the calculator can do that for you and do it more efficiently. Efficiency is, of course, important when you're sitting the exam and you've got to answer 110 marks worth of things in 2 hours. You want to be as efficient as possible. Okay, so yeah, those are those connections there. And just going to have a quick look then at modulus and argument form and exponential form in slightly a bit more detail, because I think it's important to understand what things are, why they work, as opposed to just using them because the formula says on the formula sheet that that's true. So just quickly looking here again at modulus argument polar form, and we have A and B here. And again, showing our argument and just noting here this time r, which is the length of that complex number, or I shouldn't say the length, the distance away from the origin. That's by definition the modulus of the complex number. And in this case here, we have the real part of this complex number is a. And we could just note, again, using right angle triangle trigonometry, we could note the real part of this a is actually the adjacent side of a right angle triangle. And so therefore the cosine of theta would equal a divided by r. And therefore the side A, the real part, would be r times the cosine of theta. And then looking at the opposite side, the imaginary part of this complex number is b. And using right angle triangle trigonometry, we could say that sine theta would equal b divided by r, because that's opposite divided by hypotenuse. And so therefore the imaginary part would be r times sine theta. So of course, when we add together a plus b times I, we would get r times the cosine of theta plus I sine theta. So just showing essentially that polar form is actually just writing it in rectangular form, but it's just writing the real part as the ratio of the sides in a triangle, and the imaginary part also, as opposed to just a movement of a certain amount of units to the right of the origin or up from the origin. That's straightforward. The one that's a bit weird though is Euler form or exponential form. And just noting, I'm just making this blink here for a little bit. The relationship shown here is that polar form, r times cosine of theta plus I times sine theta, is equal to r times e to the power of I theta. And this is really an interesting one if you've thought about it, because we're connecting here sinusoidal functions, or a combination of two sinusoidal functions, and saying it's equal to an exponential function. And that's quite an interesting thing to be able to say. And the proof of that is quite complicated, but we'll just have a quick look at this here, because this was first postulated by Leonhard Euler back in the 1700s. As I've said, one of the most awesome guys ever. And just quickly showing you what he did, how he was able to go about this. And he said, well, what he would have done is looked at a lot of examples of cosine theta plus I sine theta, and would have thought, this looks like e to the power of something. This looks like an exponential function. So I'm going to say, well, what if it was? Let's suppose that e to the power of I times theta did equal cosine theta times I sine theta. what does that mean? And he was able to prove something about both of them that showed that saying this was true. So he said, if these are equal, which is what he said for a start, that means their derivatives must be equal. So he wrote then the derivative of e to the I theta, the derivative of e to the power of I times theta with respect to theta must be equal to the derivative of theta with respect to theta of cosine theta plus I times sine theta. And you may or may not have got to the calculus part of this course. If you have, you'll know what I'm about to say here. If you haven't, that's okay, but just take this as being as a fact. If we differentiate e to the power of I times theta, just noting on the left-hand side, we get I times e to the power of I times theta. On the right-hand side, if we differentiate cosine theta, we get negative sine theta. If we differentiate sine theta, we get cosine theta. So by differentiating them, this must be true. But now we can go back to what we said in the first place. Well, we've said, in this case, e to the power of I theta equals cosine theta plus I sine theta. That means I could substitute that here in place of this. And so I could write on the left-hand side, I times cosine theta plus I sine theta equals negative sine theta plus I times cosine theta. Then we could expand the brackets on the left-hand side, and we would have I times cosine theta plus I squared times sine theta on the left-hand side. And we could note the thing that this all hinges on, that Leonard Euler also came up with, is the whole definition of an imaginary number and why complex numbers are a thing. I squared equals -1. So that allows us to put a -1 in place of I squared here. That's actually just negative sine theta, and we're adding to that I times cosine theta. And then we can see the left-hand side equals the right-hand side. The derivatives are equal, therefore the original functions are equal. So this proves, somehow, amazingly, without us even being able to imagine it, e to the power of I theta does equal cosine theta plus I times sine theta. So that's why exponential form or Euler form works. And it's good for us because in our course, particularly more than AA, we use exponential form a lot. And the reason for that is, as you'll know if you've been through this part of the course, we do a lot of multiplying complex numbers and a lot of powers of complex numbers. And when you're multiplying something or putting it to a power, it's much easier to multiply exponents than it is to multiply out two-part trigonometric functions, because we've got the rule a to the power of m times a to the power of n equals a to the power of m plus n. So that's very straightforward. So the power of using Euler form is very strong for making easy manipulation. So let's get into some questions now. And this first one here is just to do a bit of conversion and powers as well and use the calculator a little bit. I wouldn't call this an exam style question at all, but it's just a quick bit of practice to warm us up. So just noting here, let's suppose we have a complex number Z1, which is written in rectangular form. And this is the square root of 2 plus the square root of 2 times I. So this isn't a complex number with a real part of square root 2 and an imaginary part of square root 2. And the question is just find Z1 to the power of 3. And what we're going to do is convert this into Euler form. So I'm just bringing up the calculator, and just go along with me here if you would like to. I'm going to a new calculation page. And at the moment, my calculator's in degrees mode. I'm just going to make sure I change that to radians mode at this stage. And I'm going to go into the home button, into settings, document settings. And you'll note here I've got real or complex set to polar, because what we're going to do just right now is convert this from rectangular form into polar form. So I've made sure that's in polar form. What that means is I could put anything in a rectangular form and the calculator will convert it to Euler form. And noting here it says polar. This is where this can get a little bit confusing sometimes. We talk about polar form as being cosine theta plus I sine theta, but really polar form means either that trigonometric or it means the exponential Euler one. And what the calculator does is when it's in polar form, it puts things in Euler form, exponential form. So just now that I've done that, I'm going back to a calculation page, and all I'm going to do is write in the complex number in rectangular form. We've got the square root of 2 plus the square root of 2. Sorry, I've got that inside the square root sign, plus the square root of 2 times I. So note there, I've just exactly written in my complex number in rectangular form. Hopefully you're following along. And when I press enter, you'll see there straight away it's given an answer in exponential form. And it always, for some reasons, writes the exponent part first, and then it writes multiplied by the modulus, which is not what we're used to. But this is basically saying here that this is 2 times e to the power of 0.7854 I. So this is a complex number with a modulus of 2 and an argument of 0.7854. So another thing that you can do with the right calculator technique here is, and you may know this, often when we're looking at complex numbers in polar form or exponential form, we really want to know the argument in terms of pi. And at the moment, we've got 0.8539. There is a relatively quick way that I like of converting this into a pi fraction. And so what I would do is I would take that argument and copy it, and then I would go into the menu number 3, numerical solve, because what I actually want to know is what's that number as a multiple of pi or a fraction of pi. So I could write that whole fraction out, that decimal, which is our argument, and I could write that's equal to n multiplied by pi, just like this, and then I could write comma n, and then what the calculator will do is tell me the value of n, so that n times pi equals that number. And you can see when I press enter, I get 0.25. So now I know that the argument of this is 0.25 pi, without having to kind of do any kind of complicated conversion in my head or something like that. And 0.25 is the same as a quarter. So I know the argument's pi over 4 and the modulus is 2. So that's useful for me. It may be for you, I don't know. Just to make sure, Tarek, we are in polar mode. Yep. So make sure if you've got the same calculator, make sure you've gone into the home button, document settings, and you've gone down to polar mode. Sorry, you've gone down to complex number mode and selected polar. So yeah, and that's so we could convert from rectangular form into polar form or Euler form. So just going back to the question here, then just noting, like, that was, if you were doing this without me talking for 40 minutes over the top of it, you could convert that from rectangular form into polar form in about 30 seconds. You could type it into your calculator, do the numerical solve on the argument, and we've just noted there that z1 equals 2e to the power of pi over 4 times I. So that's a very quick process normally, trust me. What we're looking for, though, is z1 to the power of 3. So just note, now we've written this in Euler form. We've got 2 times e to the power of pi over 4 times I, all to the power of 3. And that means we've got, in brackets, 2 to the power of 3. We've also got e to the power of pi over 4i to the power of 3. So just noting that here on the right-hand side. 2 to the power of 3 is 8. And what we can do with the second part of this is just note this rule for exponents. A to the power of m, all to the power of n is just a to the power of m times n. So therefore, what we're going to have up here is just 3 times pi over 4i, which is 3 pi over 4 times I. So we can say quite quickly from there that this is a complex number, z1 cubed, with a modulus of 8 and an argument of 3 pi over 4. So this is really just to illustrate the usefulness when you're doing a power of a complex number of writing in Euler form, because you can just always use this rule, a to the power of m to the power of n. It's a very quick one. Tarek, are you using the TI Inspire? Because if you are, that's interesting. I always get decimals. I never get multiples of pi. But if you're getting multiples of pi, that's a good thing, because multiples of pi are much more useful than decimals. I don't know how to fix that, to be honest. So just quickly now, I'm going to go back to the calculator, because we've just written here z1 cubed equals 8 times e to the power of 3 over pi over 4 times I. And what we want to do is write down z1 cubed. We were given the question in rectangular form, so we should always answer in rectangular form. It's just another good idea in the exams. Whatever form you're given a question in, you should be answering in that form. So just noting here, this was our complex number. Well, I'll just write it down here. Our complex number, we have 8 times e to the power of, and then we have the fraction 3 pi over 4, and that's multiplied by I. And what we want to do is just convert that number back to rectangular form. So if I go back into the menu, documents, settings, document settings, now real complex, I'll change that back to rectangular form. Now it's going to convert anything into rectangular form. And this is where I've just written in this, remember, is z1 cubed. And if I just now press enter, you'll see it's given me my answer in rectangular form. And this is a point here at the end of the question. This is, I think, what was it Cassandra asked earlier. This is a point here where you would definitely round to 3 significant figures. And if you then carried on from there, you'd have no problem at all. This would be negative 5.66 plus 5.66i. And so just noting that down here, and that would be correct to 3 significant figures. And that would be the answer to this question. Now, as I mentioned, that's not an exam type of question. It was just to show kind of changing into polar form, how you could then find the argument as a multiple of pi and changing back to rectangular form. Of course, in an exam, if you were asked this question here, we're in rectangular form on the calculator at the moment, note. If I just took square root of 2 plus square root of 2 times I, and I mean, I could literally just write that in rectangular form inside a bracket and put that to the power of 3. Sorry, I haven't got the power of 3 there. And I would get the power of 3 in rectangular form without having to do any work. So just noting that's what you would do if you needed to do that. That was really just to illustrate how you can convert to polar form and then back to rectangular form and deal with the argument if you want the argument as a multiple of pi. Whereas Tarek's already got his as a multiple of pi by default, which is a brilliant thing, I think. So let's get into a couple of exam style questions then. And just noting here, for the first one, we're going to look at multiplying and dividing, and we'll bring in an exam style question for this. And then we're going to look at adding and subtracting, and we'll look at that with a different exam style question. So here's two complex, what we wouldn't actually call these complex numbers. These are complex functions of time. So just noting here, we've got Z1 equals 3 times the cosine of 2t plus I times sine 2t. That's a complex function of t because the argument is not a number, it's in terms of t. And this is where really knowing how to use complex numbers in Euler form or exponential form is really good, because you can't just multiply two things together and get an answer if the arguments aren't actual numbers. If they've got variables in them, the calculator just won't do it. So the second complex function here is 2 times the cosine of 3t plus I sine 3t. The question could be this: at what time, so this is a function of t where t is greater than 0, at what time is the product z1 times z2 first a real number? And I've just noted here in green, this could be a paper 1 question, absolutely, and it would be a 6-mark paper 1 question. Because they're expecting a few skills from you here. You need to be able to find an expression for z1 times z2, and unless you convert to Euler form, that would be quite difficult. So you would be expected to convert this to Euler form and then interpret what does it mean when the first time they are a real number. What does that actually mean? And how do I find that and give an answer in terms of t? So there's a few parts to this question that would make it a good paper 1 6-mark question. So just noting here, the first thing you would see when you saw this question would be we need an expression for z1 times z2. Noting here that these complex functions are both given in polar form, and so the instinct might be to say we have to multiply these two together. So just noting here, you would say that, and there's nothing wrong with this, this is correct. Z1 times Z2 equals 3 times the cosine of 2t plus I times sine 2t multiplied by 2 times the cosine of 3t plus I times sine 3t. You would notice at this point, though, hey, that this is very difficult to multiply. You would be multiplying everything in the first bracket by everything in the second bracket. You'd end up with a cos 2t times a cos 3t, a sine 2t times a sine 3t, and the calculator wouldn't do it for you because it's got a variable in there. So that's going to be very difficult. So what we would do in this case is convert them first into Euler form. That would be the first step for a mark or two. And just noting, we know for this first complex number, it has a modulus of 3 and it has an argument of 2t. So that means straight away we can just say very quickly, z1 equals 3 times e to the power of 2ti. We could then note the second complex number has a modulus of 2 and it has an argument of 3t. So we can say very quickly, z2 equals 2e to the power of 3ti. And now we could say, well, we need to multiply together z1 and z2. We're just multiplying together these two complex numbers or complex functions. And as mentioned, that is very easy. This one here, very not easy, because it's multiplying out brackets with weird things in them. So let's just go to a next step here. This is going to disappear a little bit. Here are our two complex numbers in Euler form or exponential form. z1 times z2 will just therefore be z1 multiplied by z2. And when we do this, we can just multiply the numbers. 3 times 2 is 6. And then we're also going to have e to the power of 2ti times e to the power of 3ti. And again, I'll emphasize this again. This is where having exponential form for complex numbers is so useful because we're multiplying two numbers here with the same base. E to the power of this times e to the power of that, and we have the rule, a to the power of m times a to the power of n equals a to the power of m plus n. All we have to do is add together the powers. 2ti plus 3ti is just 5ti. So now we have an expression for z1 times z2 in exponential form. It's just 6e to the power of 5 times t times I. So if we got to that point, we would now have 3 or 4 marks from this question. We've converted, we've multiplied, we've come up with a simplified answer. We now have to get an understanding of when is this product that we've just created first a real number? So when is this a real number? And so this is where we can think about this geometrically. So bringing up an Argand diagram here, and when is this real? When it's real, it must be sitting on the real axis. So just not putting here this big red arrow through the middle. Some complex number or function has to be sitting right on that axis for it to be real. If it's even a millimeter off it, it's got an imaginary part, it's not real. So we have to think, what is going to make the complex number real? How are we going to make it sit on the real axis? So just noting here for a start, when t equals 0, we're noting that, as I mentioned on the previous slide, these are functions of time. T is time, and we're looking at when t is greater than 0. We'll just put here when t equals 0, we're right at this point here. So just noting, if we put t equals 0 into our function here, we would have 6 times e to the power of 0. E to the power of 0 equals 1. So the product would just be 6 when t equals 0. And we're looking for the next time after this when the complex number is going to be on the real axis. Noting that as the value of t increases, the argument increases, but the modulus never changes. So what happens is, if you just have a look at the diagram, the complex number as t increases just goes in a circle anti-clockwise about the origin. And so where that arrow stops right there, that's the first time that the complex number z1 times z2 is real. That's the first time it's on the real axis with no imaginary part at all. And we have to think about the argument of it. So just noting here in green, once we've got around that far, we've gone through an argument of pi. So we've gone exactly half a circle, a full circle is 2 pi. So we've gone pi. So to answer this question, we need the argument to be equal to pi. Noting that our argument is 5 times t, always the number and the exponent being multiplied by I. So we've just noted here, when t equals pi, z1 times z2 is a real number for the first time. And all we need to do now is rearrange this to make t the subject. So we can divide 5 to the right-hand side. Just noting here, that will give us t equals pi over 5. So just highlighting that would be our answer to this. That would be a 6-mark paper 1 question. When t equals pi over 5, the product z1 times z2 is a real number for the first time. So there's a variety of questions that could be asked like that, which we're not going to go through all of those today. This was an example, but just to highlight at this point, because we've got a little bit of time, the question was, when is this first a real number? This question could have asked, when is z1 times z2 first an imaginary number? So just note, always, Tarek, when you're in Euler form, you write it in the form r times e to the power of theta times I. So it's the argument times I. So noting the letter I is not part of the argument. It's just what the argument is getting multiplied by. Yeah, so definitely ignore the I. So I was just saying there that this question could have said, instead of when is it first a real number, it could have said, when is it first an imaginary number? And just note, if we were trying to make this product imaginary, it would have to be sitting on the vertical axis. So that would be when the argument was pi over 2, or for example, later on, when the argument is 3 pi over 2. So a similar principle, finding when a function is completely real or completely imaginary, but it's just when it's completely imaginary, it's going to be a multiple of pi over 2. So keep that in mind. The other thing to note here is that we looked at a product, and that we're not doing an example of dividing today or quotients, but the reason we got to this point here was because when we multiplied 2ti, e to the power of 2ti times e to the power of 3 times t times I, we just added the exponents. If this was a division question, for example, when is z1 divided by z2 first an imaginary number, that means we would have e to the power of 2ti divided by e to the power of 3ti, and then our exponent would just be 2ti minus 3ti, using the rule that a to the power of m divided by a to the power of n would equal a to the power of m minus n. So yeah, just note that that particular example there gives you a window into all the things you can do with multiplying and dividing and finding when a function is real or imaginary. The key point, as it is to a lot of what we do with complex numbers in this course, particularly in context, is putting it in Euler form. So let's move on to kind of a much more comprehensive question. And you might want to just take a time to read this one. I'll read through it as well. So this question you see here is, well, this is one that we've created for the Revision Village website. This is a paper 2 question. Obviously, it's worth 15 marks. And this would be considered a very difficult question. So this would be kind of like if you saw this on the Revision Village website, where it will be probably in a month or two from now once we've developed that onto the website. So you're seeing this before anyone else does. When you see this, this is like what we would have as a red difficult question. So it's a paper 2, obviously calculated question, a difficult one worth 15 marks. And the IB do like these kinds of questions. They like questions where you're having to add or subtract sinusoidal functions, and they like to either tell you that you have to use complex numbers to add or subtract them, or not to use complex numbers. There was an example in the May 2023 exams where they had the sum of two sinusoidal functions, and they said specifically to use your graphical display calculator to find the answer, whereas sometimes, and you'll see in this question here, there's guidance in this that is telling you specifically to use complex numbers to answer this question. And there's a variety of contexts these come up in. If you've looked at past papers, you'll see that it's very common to get a question about connecting two like AC electrical sources in the same circuit and seeing what the total voltage is, or maybe having a low tide and a high tide, and the difference between a high tide and a low tide, which are both sinusoidal functions, or the difference between sunset and sunrise. Those are also sums and differences of sinusoidal functions. So the key point is when you get a question about sinusoidal functions and adding or subtract them in an exam, it's always got to have the same frequency or the same period. So noting here we've got a period of 30, that's our coefficient of t. And another example that hasn't come up a lot in exams but is likely to come up is things that happen annually. So over a year, things happen seasonally. And so if you get sinusoidal functions having in an annual time, over the period of a year, they will always have the same periods. They'll have a period of 360 days or 12 months. And so we've got an example like that here. So let's just have a read through of this question. And this one's about not a natural phenomena, it's about human phenomena, which is seasonal as well, not by accident either, because people tend to do more things outside when it's summer and less things outside when it's winter. So cafes and the like make a lot more money in summer than they do in winter. So those profits and revenues tend to be sinusoidal. So this one here says a beachside cafe operates all year round, but they've noticed that they're losing money at certain times of year. And they've said that the revenue of the cafe can be expressed as this: R for revenue. R of t equals 8,000 times the cosine of 30t plus 12,000, where t is greater than or equal to 0 and less than or equal to 12. So just pausing here again, what we could note is that this is sinusoidal, noting here that t is between 0 and 12, so we can assume from this that t is time in months. Well, we don't actually assume it, actually it says here, where t is the number of months since January 1st. So this is 12 months, it's over the course of a year. We could also note here, just from noting the coefficient of t being 30, this is in degrees. So 30 degrees times 12 equals 360 degrees for one full period. So this is not stated explicitly, but we would note if we were doing something on the graphical display calculator with this, we'd need to have our calculator in degrees. Just moving on anyway, we also have the running costs of the cafe, C for costs, which is 4,000 times the cosine of 30t minus 60 plus 6,000, again for 0 less than or equal to t less than or equal to 12. So we have a cost function, which is sinusoidal, and a revenue function with this, which is sinusoidal. What they've said next, however, is the important part. The profit of the cafe, P of t, can be expressed as the real part of Z1 minus Z2 plus 6,000, where Z1 and Z2 are complex functions of t, complex time functions. So we've been guided here to having to use complex numbers to answer this question. And we're looking for a profit equation. So let's just work through part A of this question first, and before we worry about part B and C. It says write down Z1 and Z2 in exponential form. All we know at this stage is that we've been told that profit can be expressed as the real part of the difference between two complex functions. Now we have to write down those complex functions in exponential form when we don't even know what those complex functions are. So let's just break this down a bit. First of all, we could note, and again, we don't make an assumption here, but we're not told this. We need to know that profit is always revenue minus cost. So revenue is money coming in, cost is money going out, therefore profit is the difference. So we have P of t equals R of t minus C of t. We have expressions here for R and t of C and t, which we could substitute in, and that's shown here. So we have R of t, and then we subtract all of this written in brackets, C of t. What we would do now is then just expand our brackets because we're subtracting everything inside the bracket here. So noting here as part of this, we've got a plus 12,000 and then we've got a minus 6,000. So we could just simplify those two constant terms and we could write 8,000 multiplied by the cosine of 30t minus 4,000 times the cosine of 30t minus 60 plus 6,000. Now we could compare this back to what we were given as our profit equation. We could note here our profit equation had a plus 6,000. That explains the plus 6,000 we've just found in our expression for P of t. So the real part of Z1 minus Z2 must be the rest of this. This must be the real part of Z1 minus Z2. So we're getting closer to identifying Z1 and Z2. And just going to underline here in the red, the first part of this, just note the first part of this is the same as the first part of our revenue equation, as expected, but noting that it is also the real part of another complex function. So just noting over here, Z1, if we just thought of the complex function Z1, which equals 8,000 times the cosine of 30t plus I times the sine of 30t, this is a complex function with a real part of 8,000 times cosine 30t and an imaginary part of 8,000 times I times the sine of 30t. So we've just noticed straight away that the real part of this complex number is equal to this part of our revenue function, therefore it is equal to this. So yeah, the tip here in the exam really would be, whatever functions you're given, just notice the sinusoidal part, whatever the coefficient of that is, that's going to be the modulus of a complex number. Whatever the value is inside your sinusoidal function, that's going to be the argument of a complex number. All you've got to notice really is whether you're dealing with a cosine function, because that's always going to be the real part of a complex function, or if you're dealing with a sine function, that's always going to be the imaginary part of a complex function. So now we'll just identify the second part of this equation down here, and underlining that, that's exactly the same as the cost function. And so we notice it's got a coefficient of 4,000. So therefore, we're looking at a complex number with a modulus of 4,000. It's got an argument of 30t minus 60. So therefore, we're looking at an argument of 30t minus 60. This is our complex number Z2. So what we could say, just noting from this then, is that the real part of Z1 would be this. The real part of Z2 would be this. And so we could say P of t equals the real part of Z1 minus the real part of Z2 plus 6,000. And when we talk about the real part of one complex number minus the real part of another one, that would be the same as the real part of a single complex number, Z1 minus Z2. So just noting here, by working through that process, we've written our expression for P of t exactly as we were required. We've identified Z1 and Z2, which is what this question is asking. But what the question is asked for is to express or write down Z1 and Z2 in exponential form. At the moment, we've got them both written in polar form. So all we have to do now is just realize the modulus and the argument and just write them down. So there's Z1, there's Z2. This is our answer here to part A of this question. So yeah, there's a few things here which are very kind of peculiar to the AIHL course. It's complicated stuff and it's contextual based. And they've given you enough information so that you would say, I recognize the connections here that you're asking for, recognize the connections between complex numbers and sinusoidal functions so that you can answer the question in the way that they've asked you to answer it. Okay, we'll move on to part B, which had the actual question part B had disappeared from the screen. It's now going to reappear, and everything else is going to disappear except Z1 and Z2. So just noting here, part B, which is halfway down the left-hand side of the screen now, we've got hence, find an expression for P of t in the form P of t equals A times the cosine of bt plus C plus D. So we were told originally that P of t was expressed as the real part of a difference between two complex numbers. Now we've been asked to write this in this form here. So we've got to now convert from complex numbers into sinusoidal functions. And the key word here, I think, is in this question is hence. When you see the word hence in an exam question, it means you have to use what was given to you previously, because there is actually a way of answering part B without using complex numbers. But because I've put the word hence in here, you have to use complex numbers. Otherwise, you're not going to get the marks. So just watch out for the word hence in an exam as well. So what we need to do really is come up with an expression for Z1 minus Z2 so that we can figure out what the real part of it is. So for a start, we could just write down what we've got over on the right-hand side there. We've got Z1 and Z2, so therefore Z1 minus Z2 is all of this part here, which is a very complicated looking complex function. And we need to know what the real part of this is. So we need to somehow get it into a form where we can identify the real part away from the imaginary part. First of all, what we'll do, and there's a process you go through in this type of question, which you can always follow the same process. The first one would be to expand the brackets on our term here that's got 30t minus 60 in brackets multiplied by I. So if I expand these brackets out, I'm going to get 30 times t times I minus 60 times I. So just note the next line of working is going to appear here. All we've done is expand the brackets on the second term. In the next line of working here now, we can use a rule that we have mentioned a couple of times in the last few slides. Just note in the second term, we've got exponential function here, and the power is a difference of two things. We've got a form of a to the power of m minus n. And that would be the same as writing a to the power of m times a to the power of negative n. So just noting this next step here, and just writing next to that in green the rule we're using here. We're actually using the rule here that a to the power of m plus n equals a to the power of m times n. We just happen to have one of those being a negative number. But it does allow us to separate this out into two separate exponential functions. E to the power of 30ti times e to the power of negative 60i is the same as e to the power of 30ti minus 60i. Why is that useful? That is useful because now we've actually got a common factor between our two terms. So just noting I'm underlining this here and this here, both of the terms have a common factor of e to the power of 30ti. Factorize this. And we could notice too, we also have a factor of 8,000 here and a factor of 4,000. There is also a common factor of 4,000, but we're just ignoring that for the way we're going about this question because we just want to focus on the complex number part. But just having identified that common factor, so we could now factorize this. So just noting we've taken out the common factor of e to the power of 30 times t times I, and in the brackets we have 8,000 minus 4,000 times e to the power of negative 60i. That's the most important part of this entire question because we're trying to write Z1 minus Z2 as a single complex function. What was stopping us from doing it was we had this variable t inside the function, inside the exponent there, which meant the calculator wouldn't be able to cope with it. The good thing is now, though, if you note by taking out that common factor, this process allowed us to do that. Now inside the brackets, we've got 8,000 minus 4,000 e to the power of negative 60i. That's a complex number inside the brackets, doesn't have a t in it, so the calculator can just change that into a single complex number now. So that will be our next step. So just getting rid of all of that. Our next step now is to just use the calculator to change this into a complex number, a single complex number in polar form. Just before we do that, there's a lot of little things to remember in here. The next thing is, as mentioned at the start of the question, the sinusoidal functions involved here are in degrees. What we're now trying to do is come up with a single complex number in polar form. So we need to have our calculator in radians mode to do this because polar form always deals with arguments in radians. So one step we have to do here as well is convert this argument into radians. At the moment, essentially, it's an argument of negative 60 degrees. But if I want to use the calculator for the next step, I have to convert that into radians. That's relatively straightforward. We just have to multiply it by pi over 180. So negative 60 multiplied by pi over 180 would just equal negative pi over 3. So this part of the equation here, e to the power of negative 60i, we can just write that as e to the power of negative pi over 3i for now. So this is where we're now going to use the calculator. We've done all the manipulation. Now we need to get this complex number, which is going to break open the question for us. So I've brought the calculation page back up, but I think I had changed my calculator into rectangular form. I now want to go back into the settings and just make sure I have changed to rectangular. I want to go back to polar form because I'm trying to work out a complex number in polar form. Okay, we're back in polar form and we're going back to a calculation page. What I want to do now is just write in 8,000 minus 4,000 times e to the power of negative pi over 3i. All this part in the brackets, I want the calculator just to tell me what is that as a single complex number in polar form. So I'll just type this in, 8,000 minus 4,000, sorry, I've written 40,000, times e to the power of negative pi over 3 multiplied by I. Okay, I'm just making sure I've written that incorrectly. When I press enter, you'll see here the calculator has written this now as a single complex number with a modulus of 6,928 and an argument of 0.5236. Just a note there, and it's related to, I think, what either Cassandra or Gemma asked earlier. At this point, I would not round to 3 significant figures because this is not my final answer. I don't want to use it to 9 significant figures either, though. So the thing that I can do here that the IB likes is I'll round this to 4 significant figures. So just noting here in our next step, in the brackets, we have written this as a single complex number to 4 significant figures, 6,928 times e to the power of 0.5236 times I. So that's the part that broke this question open, because now we can multiply this out and we can just write a single complex number and identify the real part. That's the whole thing of this. One more step though, recalling, as we said before, this question's in degrees. We had to convert to radians to do that step. Now we've got to convert back to degrees before we carry on. So we can't forget to do that. So converting back into degrees, that's the opposite of converting to radians. We can just multiply by 180 over pi. So I'm going to bring up the calculator again. And just note, we're converting this argument from from radians back to degrees. So all I'm going to do is I'm going to grab that whole argument, not with the I, copy it. I'm going to paste it down here, and then I'm going to multiply that by 180 divided by pi, and that will convert it back into degrees for me. And that's nice, that equals exactly 30 degrees. So I can put 30 now into my exponent. So just noting here in our next step, finally, we've got, well, I shouldn't say finally because we've got one more step to go before I can say finally. We've written Z1 minus Z2 as e to the power of 30 times t times I times 6,928 times e to the power of 30i. But what we can do now is multiply out the brackets. And just noting here, we're going to have e to the power of this multiplied by e to the power of this. Therefore, we can just write that as e to the power of that plus that. Again, using this rule's coming up all the time. The most important rule in Euler form for complex numbers, a to the power of m times a to the power of n equals a to the power of m plus n. So we've got 6,928 times e to the power of 30ti plus 30i. And just going to a new page because we've filled this one up again. What we want to do now is 2 more steps. I promise you there's only 2 more steps to this, maybe 3. We want to now convert this into polar form, like the cosine theta plus I sine theta one. So 2 steps for that. For a start, just noting here, we've got 2 terms in our exponent, and we've got a common factor of I. So we'll factorize this. That means we can finally identify the argument of this. We've got, just by taking out that common factor of I, Z1 minus Z2 is a single complex function with a modulus of 6,928 and an argument of 30t plus 30. That means we can write it in polar form. So just noting here, in polar form, it looks like this. Here's our modulus. And now I've rounded this now to 3 significant figures because there's no more calculation to be done. 3 significant figures, that's our modulus. Inside the brackets here, there's our argument. So that's Z1 minus Z2. Now, just noting, we're trying to write this as a cosine function, and it's the real part of this complex number. Just underlining here the real part. So that's the real part of the complex number. 6,930 times the cosine of 30t plus 30. So that is the real part of Z1 minus Z2. That means we can substitute all of that into this part of the expression for the profit. So just writing down the bottom of the screen now, that's our profit equation. And just noting now, we're exactly in the form we were asked for. We were asked to write the profit equation as P of t equals A times the cosine of BT plus C plus D. We have this here. We have the value of A is 6,930. The value of B is 30. The value of C is 30. And the value of D is 6,000. So that would be our final answer to that question. And we've put there a 6 mark. That's a 6 mark question. That could possibly be a 7 mark question, but I think generally speaking, if you have to find the real or imaginary part of a sum or difference of complex numbers in an exam, a paper 2 exam, generally speaking, it's worth 6 marks. So just noting that would be our answer there. Okay, there's one more part to this question, and we'll get to that in 1 second. I'm just reminding myself at the moment with this slide here, there is a feedback form for each of these sessions. So you can say what if you were happy with the session, whether you'd like to see other sessions that are similar. So just in the webinar chat, I've just posted the Google form for feedback, which goes directly to Revision Village. So just remember at the end of the session, or whenever you like, just to fill in that feedback form. And then, so we'll just go back to our question here. So we're recalling here, we've got our profit function now, and I'll just skip forward a couple of slides. So the last part of this question is to determine which months the cafe should stay closed. And just noting, we got one more piece of information here. The cafe is projected to make less than $2,000 profit in a month sometimes, and the owner decides if it is going to make less than $2,000 in a month, they're just going to remain closed. So we've got to determine when should the cafe stay closed and when should it be open. So what we've got from part B is a profit equation. And that's the key here because we need to know when is that profit equation going to work out to less than $2,000. So here's our profit equation that we worked out in part B. And the question then is, when will P of t be less than 2,000? Because that's when they should be closed. So another very common calculator technique which is used in our course then is what we can do here is we could sketch our function for P of t and we could sketch the function for 2,000. And then we could just see when is the function for our profit below the function for our of 2,000. So I'll just bring up the calculator here again one more time. Just putting up here so it's kind of out of the way. So what we would do here is go into a new calculation page. And again, recalling that this question was defined in terms of an angle in degrees. So we have to change our calculator into degrees mode. And what we're going to do is type in our profit function. So just noting up here, we're going to have 6,930 multiplied by the cosine of, in brackets. Just noting inside the cosine function here too, we have 30t plus 30. We have to put in a function of x. So we'll put 30x plus 30. Just noting that when we sketch this, x is going to represent time in months. And then we add to that 6,000. So that's our profit function right there. When we press enter, that will get sketched. And as you can see, it looks horrible. It doesn't look helpful at all because our window is not correct. So we need to adjust our window. So just going into the menu, window zoom, window settings. And we could put here, because recalling x is representing time in months, and it's going from the start of month 1 or month 0 to the end of month 12. So our x min max should be 0 to 12. Now we need to just look at the y minimum and maximum. So we could play around with this a little bit, or we could note that we've got a sinusoidal function here with an amplitude of 6,930. and a principal axis at 6,000. So the value 6,000 is going to be halfway up in terms of the y-axis up our graph, and it's going to go up another 6,930 from that. So we do know, I'll just go to the y maximum. We do know that if we put 13,000 here, we'll see the top of the graph, because the top of the graph is going to be at 12,930. Just for the y minimum, this is going to be, sorry, what have I done there? I should put this back to auto. For the y minimum, it's going to be at 6,000 minus 6,930. So for the y minimum, for example, if we put negative 2,000, we'll know we're going to see the bottom of the graph. So just pressing OK, we get a good look at the profit function now. So we could note from this, for example, in month 0, which is January, their profits are very high, and then their profits come down. And we can see here, there's a point where it's below the x-axis. In this region here, the cafe is actually losing money, so their profit is negative. And then they get a maximum point up here, which looks like somewhere around November, December. This would actually be a profit function for a cafe in the Southern Hemisphere because they have summer in December, January, as opposed to the Northern Hemisphere. What we're looking for, though, is when is this profit function less than 2,000? So then if we go into the menu, graph entry edit, we just enter another function, the function 2,000. And we can see here that horizontal red line is when the profit is exactly 2,000. So it's in between these two values when the profit of the cafe is below $2,000. So we need to find those points of intersection. And yeah, if you use the TI Inspire, you'll know how to do this. You just go into Analyze Graph, number 4 for an intersection. Calculator asks for a lower bound, so we bring our vertical line across to the left of where we see the intersection point and click. Then the calculator asks for an upper bound, so we bring it along to the right-hand side, and we get this number here, 3.18, and then 2e plus 3. So I'll just right-click on the y coordinate because I don't want that in standard form. If I go to attributes and increase the accuracy to 4, that's better. Now what it's telling me is when the time is exactly 3.18 months, the profit gets to 2,000 and it's about to drop below $2,000. So now we need to find the second intersection point, just going to the menu, number 6, Analyze Graph, and selecting number 4 for an intersection. And then we can go to the left and click over to the right, and we get the coordinates of the second intersection point. And I'll again just change the y coordinate into a normal number. So the profits start to come back up above $2,000 a month after 6.82 months. So that's the information we need to know there. And I'll just put a graph of that intersection points up on the screen. And the question part C says, determine which months the cafe should stay closed. So we need to interpret this in context in a way that is reasonable. And there may be more than one way of doing that. But what we could note here is that the month of January would be from 0 to 1. So any time between t equals 0 and 1, that's January. And then any time between t equals 1 and 2, that would be February. Any time between t equals 2 and t equals 3, that's March. Noting that our profits don't dip below 2,000 until 3.18. That's after the end of March. It's somewhere at the start of April. 3.18 would work out roughly to about April the 5th. So it's about April the 5th or 6th that the profits dip below 2,000. And then we can note, so when t equals 3, 3 to 4, that's April, 4 to 5 is May, 5 to 6 is June, 6 to 7 is July. So 6.82, when the profits start coming back up above $2,000, that's at the end of July. So 0.82 is about 24, 25 days. So we could actually identify roughly down to a day. Bearing in mind this is just a mathematical model, it's approximation. Approximately from April 5th until about July 25th, the profits are below $2,000, and so really the cafe should stay closed. So the question I asked, determine which months the cafe should stay closed. It didn't say the dates, it just said the months. So our recommendation based on this would be the cafe should stay closed for April, May, June, and July. So just noting here, this would be our answer in context to that question. The cafe should stay closed during April, May, June, and July. Okay, so that's the end of that question. So that involves the difference between two complex numbers and how they relate to sinusoidal functions. Oh yeah, fair question, Tara. But I was just kind of saying, maybe I'll try and write on the screen here, because the value of t we're thinking of, or you're thinking of, is discrete, like as in whole numbers, but the time is continuous. I'll just see if I can write up here. If t is anywhere between 0 and 1, that whole region would be January. Anything between 0 and 1, because there's decimals, right? So 0.1 would be in January, 0.9 would be in January. Once we get to 1, and I'll just make sure I'm not crossing over my inequalities here. Let's say when t is between 1 and 2, that's February. So you could say, for example, any time t that starts with a 1 is in February. Any time that starts with a 0 is in January. Any time that starts with a 2. So if the value of t is between 2 and 3, that's March. So you've just got to be careful. Make sure you put it in context, and ask yourself, what does this value mean if I put it into the context? So as soon as you get to the number 1, you're finished January, you're starting February. As soon as you get to the number 2, you're finished February, you're starting March. As soon as you get to the number 3, you've finished March, you're into April. So 3.18 is in April. Hopefully that answers the question. So just noting, a t value between 2 and 3 is going to be March. So the one we've got here, 3.18, that's for a value of t between 3 and 4, which is going to be April. So yeah, it could catch you out a little bit. Just be a little bit careful with that. So, and it's a good example there. It's the kind of little thing that IB like to throw in as a contextual, just to make sure that you do get a lot of kind of brilliant math students. You can't catch them out mathematically, but maybe sometimes they don't quite map the mathematics onto the context quite exactly right. And yeah, if you put down March for this question, you would lose a mark, because definitely, because we get all the way to a value of t equals 3 without going below the line, we can say for sure the whole of March profits above $2,000. So yeah, be careful with that one. Okay, so yeah, good question. Thanks for that. We are perfect. Thank you very much. Okay, cool. Sorry, I probably carried on a bit longer than you needed. My questions hadn't scrolled up. That's great. Okay, I'm just going to say one more thing. That was we've done a paper 1 question and a paper 2 question. I just wanted to mention one more thing, which is not necessarily part of this session, but it is related. Maybe I'll just wrap this up quickly, and then I'll come back to it in case anyone doesn't want to see this. But as I'd mentioned, like this is doing the difference between two sinusoidal functions as complex numbers. For the first time in the May 2023 exams, the IB asked one of these where they specifically wanted students to do it without using complex numbers. There was a difference between two sinusoidal functions. So I just want to kind of show you how you could have done this one without using complex numbers. So, I'll come back to that in a minute. I just want to note here, this is kind of the end of the session wrap up. We kind of had a look at the start at reviewing conversion between Cartesian, polar, and exponential forms, and we looked at a product and an integer power. And I noted there that quotients are the same as products because we put them in Euler form and then we subtract the powers instead of adding them. We've looked at sums and differences specifically in the case of sinusoidal functions, again using complex numbers in Euler form, which is something that IB love to throw into their exams. Paper 1, paper 2, paper 3, they'll put it anywhere, they love it. And so, yeah, we looked at paper 1 and paper 2, and there were a few calculated techniques in there, maybe converting between the different forms, maybe using the numerical solver to find, in terms of pi, an argument, and of course, putting a number like 8,000 plus 4,000 e to the power of 0.5236i into one single complex number so that you could then find the real part of it. I will say at this point, thank you for coming and good luck for your exams if you're sitting the November exams. At this point, I'm going to go back and just look at that previous question, just using sinusoidal functions instead of complex numbers. And once we've done that, I will be staying on the line for another 10 or 15 minutes in case anyone has any other questions that you'd like answered if they weren't necessarily specifically related to those questions. Cool. Okay, I'm just coming back to this question here. Oops, sorry. I'll go back a couple of slides, I think, where this is a bit blanker. So just noting this question here, with the one we just did, say part B, we had to write P of t as a cosine function. And we were guided specifically to do that with complex numbers. But it could be in the exam, the IB might have said, use your graphical display calculator to find PT in this form, in which case they would be guiding you not to use complex numbers, but to use graphs. So just noting here, I'm going to just get rid of that graph. And I'll go to a new graphing page. Hang on, hitting all the wrong buttons. Yeah, if I go to a new graphing page, and just note, what we could note here is that P of t was literally the difference between the revenue and the cost. So we could have written into the calculator exactly what we see here, that minus that. So I'm just going to do that now. I'm going to type in here 8,000 multiplied by the cosine of 30x, and then subtract from that the cost equation in brackets, 4,000 multiplied by the cosine of 30x minus 60. And that was plus 6,000. I think I've forgotten something here too. Yeah, sorry. The revenue function had a plus 12,000 after the cosine function. And then we had minus the entire cost function had a plus 6,000 after the cosine function. And then the brackets were closed around that. So if I press enter here, just note, I'm going to get, again, the window's wrong, so this looks horrible. I'm going to get one single sinusoidal function, r of t minus c of t, which is equal to p of t. So I'll just quickly adjust the window of this one. Going back to the window zoom, window settings, we know the x minimum 0, the x maximum is 12. For this one here, because we used this before, we can say the y minimum is 2,000. And the y maximum is 13,000. Well, that's for our window. So just see here, this graph you can see on the screen is identical to the graph we came up with in part B. We came up with that using complex numbers because it's a good method for doing it. But no, we could have come up with exactly that graph just by literally typing in P of t equals r of t minus c of t. And then the task would be to somehow write the equation of this as one single sinusoidal function, because at the moment here, this is written just as the difference of two sinusoidal functions. And it would be a matter of finding the value of A and the value of B, the value of C and the value of D. Three of those are very straightforward. One is that we could definitely say it right at the start that B equals 30, because just noting when you add or subtract two sinusoidal functions, if they have the same period or the same frequency, the sum or difference must have the same frequency or period. So we could say without doing any work that the value of B in this must be 30. The second thing that would be very straightforward to do is find the value of A, because A is the amplitude of the function, and we do this in AISL as well. Amplitude of a function is always the max value of the function minus the minimum value of the function divided by 2. Yeah, max minus min divided by 2. So we could have on the calculator here, for example, just gone to analyze graph, selected 3 for a maximum, found the maximum of the function, which we could see there is at 11, well, exactly at a height of 11, x coordinates 11, sorry, the y coordinates 1,290. So this function here's got a maximum of 1,290. Sorry, that's 12,900. I really should convert that before I start talking about it. Let's just, yeah, there we go. That's better. The maximum of this function for profit is 12,928. Oh, sorry, I've just seen another question here. These aren't updating on my screen. Can you remind me why minimum is minus 2,000? Now, when we did this before and came up with the function using complex numbers, what we noted was that the actual, I'll go back to this on the screen here before we carry on. Where is our answer? Yeah, there's our answer. So just note here, this is what we came up with, Tarek, before we sketched it. And the reason we know y min is 2,000 is because just noting here, for any sinusoidal function, this constant here, that's the principal axis. That's the principal axis of a sinusoidal function. And what happens is the maximum of a sinusoidal function is always the principal axis plus the amplitude. So you go up 6,930 plus 6,000, and I know the maximum is going to be there without doing any calculation. The y minimum is what you asked, though. Why did I put y minimum 2,000? That's because I know the principal axis is 6,000, and I know the minimum must be when I start at the principal axis and subtract the amplitude. So it wasn't necessarily that the y minimum was 2,000 for any particular reason. It was just that I knew the minimum of the graph was going to be at 6,000 minus 6,930. The minimum was going to be at negative 930. So I just wanted to make sure I could see the bottom of the graph, and the value negative 2,000 is less than negative 930. So it was just a good number to put in as y min. Yeah, so that, and it's just the point that once you've got a sinusoidal function equation, by looking at the amplitude and the principal axis, you know exactly where the minimum and maximum are going to be. So you know exactly what you can put in for your y min and y max and be able to see the top and bottom of the graph. Okay, I'm just going to go back to that graph we were drawing. So as mentioned here, and this is actually related to what exactly Tarek just asked there. So we've identified the maximum point of this function at 12,928. We could also identify the minimum point of this function, which is down here, and it should be at negative 928 because it's going to be at the principal axis minus the amplitude. But doing it this way around, we didn't know what the amplitude or the principal axis was. We're doing this the other way around. Rather than using the amplitude and the principal axis to find the minimum and maximum, we're using the minimum and maximum to find the principal axis and the amplitude. So yeah, again, if we were doing this without using complex numbers, we could sketch that graph. We could see the maximums at 12,928, the minimums at negative 928. And so therefore we can say from that, the amplitude of this is going to be maximum minus minimum divided by 2. 12,928 minus negative 928 divided by 2. And that would equal 6,930. So we would know the value of A is 6,930. As mentioned, we know the value of B must be 30 because it was in the original functions. And we could also note the principal axis is going to be minimum plus maximum divided by 2. 12,928 plus negative 928 divided by 2, that equals exactly 6,000. So very straightforward to find the values of A, B, and D. The only thing that would be slightly more complicated is then to find the value of C, which would be the phase shift for this difference. And the phase shift is just essentially how far would a normal cosine function have been translated to the left or right in order to make this function. So what I would do if I was doing this is I would, and I think I've done this in a video for the past papers, I would draw on here a normal cosine function, if you like. And when I say a normal one, I would just mean one with the same amplitude as this, the same frequency, the same principal axis, but no phase shift. So I'm just going to go into the menu, graph entry, edit, and I'm going to type in the function here, 6,930 multiplied by the cosine of 30x plus 6,000. So this is the same function, but without any phase shift. And I can see it looks like that. And all I would have to do here is take the maximum value of this and see how far would I have to shift that to map it onto the maximum value of our particular function here. And so if I did that in this case, what we would find is that the phase shift, because this one would have a maximum occurring exactly at 12, and it would have to be shifted exactly 1 month to the left in order to map onto our function, which is it's got its maximum at 11. So it would be a phase shift to the left, which for a start, in terms of transformations of functions, means a positive value for the phase shift. And then the next thing we would note is that when we shift 1 month out of 12, that would tell us that we are going to have a shift of 1/12 of a full period of 360. 1/12 of 360 is 30. So that would be how we could find out that the phase shift should be positive 30, because it's essentially here a shift of 30 degrees to the left. So there is a way of finding that value function P of t just by using sinusoidal functions on the graph page without using complex numbers. But it's just raising the point. Sometimes the IB will force you to do it using complex numbers because that's a skill they're testing. Sometimes they'll get you to do it by using the graphical display calculator because that's the skill they want to test. Anyway, that's the end of this session. As mentioned, I'll be online here for another 10 minutes because this session is scheduled to go until hour. So if anyone has any questions, I'll be waiting here. If no one has any questions, good luck for your exams. Thank you for coming. So Tarek's just asked, any other tips for complex numbers or sinusoidal functions in the IB exam? Yep. My best tip for any of these topics really, but and especially for these ones is, really you need to understand the topic. Like you've got to do as many different questions as you can related to these topics, but also just make sure you understand why each step works, what that step is doing. If you're using formulae, make sure you understand what the formula is and why it works. And always think about the context of it. And what does this actually mean in context? The IB will always, I shouldn't say always, but almost always put these in a context, whether it's profit and cost or whether it's tides or sunset, sunrise. Like think about the answer in context. What does this mean in context? If I drew this graph, what does this graph mean in context? Because the more you ask yourself about like what the numbers mean conceptually as well as contextually, the more it aids your understanding of that. And the thing is, if you understand something 100%, you can't really get caught out on it. So understanding is key. The other thing I'd say about complex numbers is it does come up in a lot of different areas of the course. Like we've really just looked at here today, how it combines with sinusoidal functions. But because a complex number has a real part and an imaginary part that can be expressed as a vector, there's a big connection between complex numbers and vectors. So, I haven't seen the IB do this yet, but I'm expecting that at some point soon they're going to do a big complicated question which combines complex numbers and vectors, which might be finding angles, or scalar products or vector products or something that's put in terms of a complex number, which could be quite interesting. So just be aware of that. Always with complex numbers too, I always draw them. If I'm answering a question about complex numbers, I always draw it so I can understand it geometrically rather than just relying on the numbers. Another place where complex numbers come up, of course, is in differential equations because they are used as, if they're the eigenvalues of a coupled system, they can help determine the answer to a differential equation, an exact solution. So make sure you think of all the ways they can come up. And that is actually related to this too. Because if you think about powers of complex numbers in Euler form, and if you sketch those, they actually spiral out from the origin. Like there's always a spiraling motion between complex numbers when you take the power of them. And that would be the same as having like the complex solution of a coupled differential equation. In some of those cases, I think where A is positive and the eigenvalues are complex, you get a phase portrait where the trajectory is a spiral out from the origin. So there are connections to be made there as well, which are always good to be aware of. There was one more connection I was thinking there as well when I said that. Because it's the IB will always stay within the curriculum, but they'll always find ways of connecting things that you may not have seen before. So it's being aware of connections between different parts of the course, and complex numbers just happens to have a lot of connections with different parts of the course. Oh yeah, I was going to say, if you add or subtract like rectangular complex numbers, they make arithmetic sequences. So there's connections between complex numbers and arithmetic sequences. If you multiply them, they make geometric sequences. So there's more connections there. So just think about all of these potential connections. But if you understand each of those topics in isolation, then the connections become more apparent and they make a bit more sense. One other tip I'd say on that stuff is something I've always done as well, is just whenever I come up for an answer, like on that, we didn't do it in that one there, but as soon as I come up with an answer, say for what a graph looks like, I would graph the original function of just r of t minus c of t, and then I would graph the function of p of t that we came up with and make sure they map exactly onto each other, because if they didn't, I'd know I'd made a mistake somewhere. Or if I found the value for t, I would substitute it back into the equation and see if it works, just to be sure about that. Thinking of any other connections with sinusoidal functions or tips for sinusoidal functions. Yes, sine functions as a tip is just always be aware of the context. Like sinusoidal functions appear in so many different ways, things that are seasonal or cyclical or throughout the day or throughout a month. And it's, just always thinking about what's the context of this and always being aware of between the written, really 100% between the written form of a sinusoidal function and the graph, just making sure that you understand what's the amplitude, what does the amplitude look like on a graph, what does it mean in terms of the written function, what does the period mean, or the frequency, what does that mean in the function, what does it mean on the graph, what does it look like, what does it mean in the context. Same with the phase shift, same with the principal axis. So yeah, just as much as you can, keep asking yourself, what does this mean? What does it look like graphically? What does it look like written down? Contextually, what does it mean? And as soon as you think about something contextually, so often you'll think in context, well, that doesn't even make sense. And then you'll know that you might have to relook at what you've done. Do I think the boundaries for this exam will be higher or lower than May? Yeah, that's a tricky one. I have no connections to the IB in which I can comment on how they come up with their boundaries. But my theory has been for the last few years that, and I could be wrong about this, that the boundaries have, in theory, should be getting slightly higher each year. And therefore, I could argue possibly the boundaries for November might be higher than they were for May, although you might view November as a different kind of completely, say, mutually exclusive subset to May in November. But when these courses first started about 3 years ago, the content was different. It was new, and the kinds of questions were different and new. And teachers took a while to get used to that. Students took a while to get used to that. So it was a lot more challenging back then. And so my theory was that I think the original grade boundaries 3 years ago were quite low. And then I think as teachers have got a better understanding of what the course is all about, and as students therefore get a better understanding of what's required, and there's more past papers available, so there's more practice material to make sure that you kind of know your stuff, then the grade boundaries get slightly higher because in theory the exams are becoming slightly easier to cope with. So I think they do get a bit higher in that respect. And it is related to the fact too, to some degree, is that even though these are criterion reference rather than norm reference, to get a 7 is saying that you are, say one of the top 5% of IB students who sit this exam. So if, and they do use this to manage things, if they write an exam that happens to be accidentally much easier than May, they'll set the boundaries way higher because they need to balance out the fact that they've set an exam too easy and people who are getting really high marks are not actually in that top kind of echelon of IB students. And the opposite of that is true. If they set the exams really hard, which I think a couple of years ago they made the exams really, really hard, and the average grades were quite low, so the grade boundaries were quite low that year. So there's a few different things to consider there. So it depends. And to be honest, it's actually an impossible question to answer, having not seen the November exams, because the key thing to the grade boundaries, and this is why they don't release them before the exams, is how hard is the exam in November going to be compared to May? And we won't know that till we see the November exam. The IB won't even know that until they see the results of the November exam, because they need to see how November students cope with it compared to how May students cope with the May exams. And yeah, so they won't even set the grade boundaries until all the November exams have been marked. So I've given a bit of a theory on what I think is happening with the exam boundaries, but yeah, no one really knows until the exams have been seen, set, and marked. Anyway, it's just ticking over 1:30, or that's in my time zone. It's ticking over half past the hour, so I'm going to sign off. So thanks for coming. Thanks for the questions. Hope I was able to help with those. Hopefully that helped with the topic. This is Clement Mustian signing off for Revision Village.